Good morning, sir.
Good morning. So, are there any questions, doubts? You may ask, please.
Sir, can we have the solution of minor paper?
Yeah, I will do that. I will send it. I'll get it scanned and send. So, okay, then let me start. Yeah, so last class I was actually discussing the frame element. So the transformation for that, that is what was left. Hello, is my screen visible?
Yes,
Hello,
sir.
okay. So last class I was discussing frame element. So we had, of course, discussed the development of element level governing equation, element level stiffness matrix, external load vector, internal load vector. And the last thing I was discussing about is the 2D transformation. For frame element. So what I had discussed was that suppose you have a frame element with certain orientation, and you have this local coordinate x and this y, and in terms of the local coordinate system you have degrees of freedom. So you have u naught 1 e, and then in this y direction you have v1 e, and then theta 1 e. So these are the degrees of freedom. This is the local node number 1, this is local node number 2, and the degrees of freedom here are u naught 2 e for the element, v2 e, and theta 2 e. So these are the degrees of freedom in the local coordinate system. And if you the same thing if you be talk in terms of the global coordinate axes. So the global coordinate axes are, let us say this is small x, small y, and of course the local coordinate axes are this capital X and capital Y. So the degrees of freedom in the global coordinate system are u capital U1e. So this was u1e. Then along y direction we had this capital V1e, and then theta 1e. Theta remains same, and then at second node you have u2e, v2e, and theta 2e. So these are the degrees of freedom in terms of global coordinate axes. So if you look at the relationship between the local and global displacements, so we have these are the global displacements. So say u1e and v1e at a particular node, either node 1 or 2, and let us say that the uh, this local x-axis is at an angle alpha with the global x-axis. So this angle is alpha, and this is v1e. So these are the degrees of freedom. So we had written no you can express this u naught 1, the displacement along local x-axis, in terms of these two displacement, this displacement and this displacement. So basically you take the component of u1e along this small u naught 1, and also component of capital v1e along this u naught 1e. So we had said that u naught 1e is equal to this u1e cos alpha plus v1e sin alpha. So this is what we had written. And similarly, the v displacement, so that is displacement along local y axis v1e can be written as minus u1e sin alpha plus v1e cos alpha. So we are basically writing these two displacement, this and this displacement in terms of these two displacement. So that is what this relationship is. So now if we look at the vector of degrees of freedom in the local coordinate system, so we look at dE. So this d is consisting of u naught 1e, v1e, theta 1e, u naught 2e, v2e, and theta 2e. So this can be written in terms of the transformation matrix. Here we have transformation matrix, and then the vector of global degrees of degrees of freedom with respect to global coordinate axes. So these degrees of freedom are basically u1e, v1e, theta is same, and then u2e, v2e, and theta 2e. So this is what we write the transformation matrix. So as per this equation, we have written u naught 1e, so that is equal to u1 e times cos alpha. So here we will have cos alpha, and then v1 e times sin alpha. So the second column would be sin alpha, and then there are no contributions from others, so we will put 0. Then v1 e is u1 e times minus sin alpha. So here we will have minus sin alpha, then cos alpha, 0 0 0 1. And then the rotation is because z axis is the same in the local coordinate system and global coordinate system. So the rotation, this is same theta 1e. So we'll have 0 0 and 1, 0 0 0. And then u2e would be similarly at the second node. So similar to first node, you will have here cos alpha, sin alpha 0, and then small v2e would be minus sin alpha cos alpha 0, and then 0 0. The theta 2e is same as theta 2e, so we get unity there. So this is what we get as the this relationship. So we write this as you can say in the notation form, d is equal to nothing but this 6 by 6 transformation matrix into vector or degree of freedom in terms of the global coordinate axes. So this is the transformation matrix, this is the global degrees of freedom, and this is the degrees of freedom with respect to local coordinate system. And you see that this is a 6 by 1 vector, the transformation matrix is a 6 by 6 matrix, and this degrees of freedom with respect to global coordinate axis is a 6 by 1 vector. So I had, I think, discussed up to here. And then now if you want to get the transfer similar to the way we did for the truss, so it is other steps are same, only thing is that the transformation matrix is different, otherwise the steps are same. So if you look at the transformed and why we need to do is this, because the different elements are oriented in different directions, so the local coordinate axes are different, so we need to transform the element level coordinate equations into a common coordinate system before assembly, and then after doing this we basically assemble. So we had seen that the transformed label no element level governing equations are, so first we write small d equal to t into d, and then pre-multiply the whole equation by t transpose, so that the element level governing equation becomes t transpose into ke into t. So we get here into t and into capital DE is equal to, we have t transpose into f external for the element, and plus we have t transpose into f internal for the element. So this becomes the transformed element level governing equation, and we have written earlier this as Ke bar into dE is equal to F external E bar and plus F internal E bar. So this we can write this equation where Ke bar is nothing but this F external bar, this, and the F internal is this whole thing. So yeah, this is what you get as the basically the transformed element level governing equations. And then we have to, of course, uh, the transform, assemble, impose the boundary conditions, and all those steps. So let me just again show you another application of this element. So I will take an example. We are taking no. So if you look at the basically a number of structures, you will have some of the structure existing inside this super submarine can be approximated using these. So this, let me take one example. So the example problem is, I'm just taking a simpler case, although you can have many complicated problems. I know any kind of a problem which is involving all the members of a frame structure in a plane. I mean, all the members, only thing is this element requires that all members should be in one plane. So this element actually can be used. So now let me take an example. Say we have this a frame. So this is the frame, and it is fixed over here, and similarly it is fixed over here. So it is fixed at these two locations, and the load are, there is a distributed load here in this direction. So this is a load, and let us say this is Q naught, and in this load is like this. Although in one there can be concentrated force and so on, but we are taking this example. This is also Q naught. They of course can be actually different. And now let us discretize this using two elements. Although no, in an actual problem you will have to discretize into a more number of elements, but for a simple case we are taking two elements. So this is, let us say here we have node 1, and here we have node global node 2, and here we have global node 3, and the elements are, this is, let us say, element number 1, and this is element number 2. And the properties of no, both these members are, so that is length is L, Young's modulus is E, cross sectional area is A, and the second moment of area is I. And similarly for this member also length is L, cross sectional area, no, Young's modulus is E, cross sectional area is A, and the area moment of inertia is I. So these are the properties, and both the members are identical here. So now the coordinate system. So let us take this as the global x-axis, and this has the global y-axis. So these are the no, global coordinate axes x and y. That we are going to keep same for the entire problem. But the local coordinate system, no, the x-axis has to be along length of the element. So this is also going to be along the x, and then let us say this is going to be capital Y. So the local x, y are, no, this is x, capital X, and this is capital Y for the first element. For the second element, the local x-axis has to be along the length of the element. So its origin, I am taking the starting node as global node number 2. So we will have capital X here, and this is capital Y. So for the element number 2, the local and the global coordinate axes are basically parallel, whereas for the first element, the local and the global coordinate axes are actually different. So here this is the structure we want to solve, and since no, you will see that now if you look at this member, there is a transverse load, but that transverse load would become an anaxial load for this, and there is a transverse load in this, and so this is subjected to axial and transverse both loads. So we need to use a frame element which has got the degrees of freedom along the length of the member, and also the transverse displacement and slope degrees of freedom. So that we need to use a frame element basically for this problem. So here if you notice that the members, both the members of the structure are identical, members are identical, and as I have already said, xy and z is same in both basically, so I'm not writing that. xy is a global coordinate system which is common for the entire problem, coordinate system, and capital XY are the local coordinate system. For we have of course orientation of capital X and capital Y coordinates are different for both the elements. So these are the local coordinate system. This is a local coordinate system. And if you look at the connectivity, in terms of the global and local nodes, so the connectivity is in the connectivity we look at the element number, so we look at the element and we also look at the nodes, though these are the local nodes. So an element number 1 has consisting of nodes, basically global nodes 1 and 2. So it is starting node, that is local node number 1 is global node number 1 and local node number 2 is global node number 2. So these are the global node numbers. And for element 2 the local node number 1 is global node 2 and local node number 2 is global node number 3 for the element number 2. So this is the connectivity. Now before we can know assemble, let's write the transformed element level stiffness matrix for both the elements. So if you look at the element 1, so we have already derived the element level stiffness matrix, we are just going to use that. So now the element number 1, if you look at it's a this is the global x-axis and this is local x-axis. The angle between these two, this is actually your alpha, and alpha is 90 degree as you see in this case. So for this case angle alpha is actually 90 degrees. And if you look at the global degrees of freedom, now if you look at just the element and its local node number 1 and 2, so the degrees of freedom are u1 and v1 e, and this is theta 1 e, and then you have basically u2 e, v2e and theta 2e. So these are the degrees of freedom in the global coordinate system. So these are global degrees of freedom, global degree of freedom, DOFs. I'm writing DOF means degrees of freedom. So DOFs means degrees of freedom. So now if you look at the transformation matrix, so alpha is 90 degrees and we have already written this. No, the transformation matrix is written over here. So this is the transformation matrix. So this is cos alpha sin alpha minus sin alpha cos alpha. So if you put alpha equal to 90 degrees, you will find that the transformation matrix T will be actually equal to cos alpha is 0 because alpha is 90 degrees, sin alpha is 1, and then we have of course the 0 0 0 0, and then we have minus sin alpha, so that is unity, cos alpha it is 0 0 0 0, and then we have 0 0 1 0 0 0. So the same thing, 0 0 0, again this is 0 and this is 1, and we have 0 0 0 minus 1 0, and then we have 0 0 0 0 and 1. So this is the transformation matrix. I leave you as an exercise to cross check the result which I am going to just write. So now if you look at this transformed stiffness matrix, that is Ke bar. So Ke bar is equal to basically T transpose into Ke into T. So you can check this result, you will find that this will be equal to no, if you multiply, you have to, now T is defined, you have to multiply all of that. So you will finally find, of course, K is no, we had given in the last class, the Ke, which was involving the stiffness matrix of two-noded truss element and a two-noded Euler Bernoulli beam element. So we combine that, we get this Ke in terms of local coordinate axes. Now we do this T transpose K into T, this transformation. So finally you will find that this comes out as 12ei by L cube 0 and minus 6ei. So this multiplication you have to do, basically T transpose K into T. So cross check this result what I am writing, and then minus 12ei by L cube 0 and then minus 6ei by L square. So that's the first row after transformation. Then the second row is 0 Ea by L 0 0 minus Ea by L and 0. And then third row is minus 6 ei by L square 0, 4 ei by L, 6 ei by L square 0, and then 2 ei by L. So this is the third row. The fourth row is then minus 12 ei by L square 0, 6 ei by this should be L cube. So minus 12 ei by L cube 0, 6 ei by L square 12 ei by L cube 0, and 6 ei by L square. Then the fifth row is 0 minus Ca by L. In this case, the transformed stiffness matrix is simpler because alpha is 90 degrees. So sine alpha is unity and cos alpha is 0. So you see that this is somewhat simpler form, 0 0, and then you have A by L 0, and then the sixth row, that is the last row, is minus 6 ei. Of course, the matrix is symmetric, so we will always find that no the symmetry, that is this ijth element would be equal to jith element. So 0, and then we have 2 ei by L, then 6 ei by L square, then 0, and then 4 ei by L. So this is a transformed stiffness matrix. So similarly, if you look at the basically the the transformed load vector, so you'll find that f external e bar, which is no we have set t transpose into f external for the element. This formula we have just written, so this would be t transpose, and f external is no you already know that for this frame element. So this is 0, there is no axial load. You will have to see here that no, this is the local y axis and the load is in the same direction. So as per this coordinate system, this q naught is positive. So and there is no distributed load along the axial direction. So qx is equal to 0 and qy is equal to q naught. So that is what is there. So you will find that this in the local coordinate system, the load vector would be q naught L by 2, q naught L square by 12, and then this term is again 0, and then we will have q naught L by 2 and q naught L square by 12 minus sign. So this is no if you again multiply it by t transpose, so finally you find that after the multiplication with the t transpose, this becomes q naught L by 2 in the global coordinate system 0, q naught L square by 12, and then minus q naught L by 2 and 0, and minus q naught L square by 12. So this is the transformed basically the external load vector which you get, and we have already said that no dE for the first element is the local the degree of freedom in the local coordinate system. So u naught 1e, v1e, theta 1e, u naught 2e, v2e, and theta 2e. So this is the vector of degrees of freedom in terms of the local coordinate system, and the global degrees of freedom vector no the degrees of freedom vector in terms of global coordinate axes is no this u1e, v1e, theta 1e. These are capital no u2e, v2e, and theta 2e. If you look at the external load vector for this the sorry the internal load vector, external load vector we have already written over here. So in terms of the global coordinate axes, you can, without going into the transformation, you can write those forces. So let us say the global forces in terms of the coordinate
Excuse
axes.
me, sir.
Yeah.
Sir,
Yes.
just now you told that we will take in the external load vector, we will take the axial load as zero, sir.
Yeah, so I have taken that, no? So that's what the in the local coordinate system, you see this term and this term, they are 0. So that is coming from no qxl by 2, qxl by 2. So qx is 0. So that is what it is 0, no? After the transformation, you get it in this manner. So when you
Sir, but
multiply this,
Sir, but if we see the frame element, sir, it is being subjected to axial load along the local coordinate x.
No, it is not. No. So if you look at this, so I'm talking about the first element. So this load Q naught, which is there, no, this one, this is along the y direction. So there is no load along the, no externally applied distributed load along the capital X direction. So as you see here in the first element, there is a load only along the global y direction. So Qy is equal to Q naught, but Qx equal to 0. No distributed load along capital X direction. This is the capital X direction. In this direction, there is no distributed load. Are you able
Yes,
to
sir. Yes, sir.
recognize that?
Yes, sir. Yes, sir.
Okay.
Thank you, sir.
Yeah. So that is how I wrote this, and then therefore finally after the transformation, of course, you get this, and you get this because because of the orientation of the coordinate axis. Then I was saying that you could also look at the transformation of the internal load vector, but then the after transformation internal load vector can be written in terms of the components of forces along the global xy and z directions. So on the first node, because the outward normal is along negative, basically local coordinate direction. So we take the forces along negative coordinate global coordinate direction. So here, let us say that we have a force in the first element. This force is along x direction. So node one for the element one, and this is the force along the global y direction. So Fy at node 1 for the element 1, and the moment is about the positive z axis, so at node 1 for the element 1. And similarly at node 2 you would have these forces as along the positive directions. So this is Fx2 for element 1. So without transformation I'm writing these forces along the global coordinate direction. This is fx2, and this would be basically fy2 for the element 1, and then you will have this m2 for the element 1. So this is the basically internal loads which would be acting on the element. So this is the transformed element level governing equations for the first element. Now if you look at the element number 2, so element number 2, because I have already said the global x-axis and the local x-axis are in the same direction, so the angle alpha is actually equal to 0. So if you look at the element 2, so for that alpha equal to 0. So if alpha equal to 0, then you would see the transformation matrix T would be identity. So it would be 1 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 0 1 0 0. So now cos alpha is then a unity, sin alpha is 0. So this is what you get as the transformation matrix. So then you will see the transformed stiffness matrix and load vectors are basically going to be same. So this is now in this case is the identity matrix. So you will find that no, when we do the multiplication, so K bar transpose will become T transpose into K into T. So that simply will become K, and F external for this element will be basically equal to F external. So this will be same as what you will have for the basically the in the local coordinate system, whatever you have. If you look at the forces, internal forces, so same way we write the forces along x and y direction. So this is the node where the outward normal is along negative global in this case negative global x direction. So we write the forces along positive forces along negative coordinate direction. So this is fx1 for the element number 2. This is fy1 for the element number 2, and then you will have moment about yeah, and the moment has to be about negative z axis. So the arrow has to be different. So this would be m12, and at this node you will have fx2 for element 2, and you will have fy2 for element 2, and the moment is m22 for element number 2. So these are the internal forces which would be acting on the element in terms of the global coordinate direction. So accordingly, you can write the internal load vector. So now if you look at the assembly, we'll have to assemble these element 1 and 2. So now if you look at the assembly, so total you see there are 3 nodes, and each node has got three global degrees of freedom in terms of the global coordinate axes. So since there are 3 nodes, there would be total 9 degrees of freedom for the element before the imposition of the boundary condition. So then the assembled stiffness matrix is going to be of size 9 by 9, and the vectors would be of size basically 9 by 1. So now if you look at, so let me write it, so it is going to be somewhat bigger. I know the stiffness matrix. Yeah, these are no some problems for which no solution can be demonstrated. Otherwise, no one has to write either the codes or use a package to solve more complicated problems. So these are somewhat simpler problems which can be, whose solution can be demonstrated. So that is why I am taking this. So this is the stiffness matrix. It is going to be of size 9 by 9, as I said, and then you have the degrees of freedom. And then you have the external load vector, and then you have the internal load vector. So this is going to be, so now if you look at degrees of freedom in terms of the global nodes, so it would be u1 v1 theta 1 for the first node in terms of the global coordinate axes. Then you will have u2 v2 theta 2 for the second node, and then u3 v3 and theta 3 for the third node. So these are the degrees of freedom. Now the assembly. So if you look at the first element, that is defined between the global nodes 1 and 2. So it's 6 by 6 matrix will go into the first 6 rows and columns of this global stiffness matrix, because the first element is defined between global nodes 1 and 2, and global node 1 correspond to these degrees of freedom u1 v1 theta 1, first 3 variables, and degrees of freedom corresponding to second node correspond to u2 v2 theta 2, that is fourth, fifth and sixth degrees of freedom. So the first element stiffness matrix will be added in the first 6 rows and columns of the global stiffness matrix. So if you see, it's the same stiffness which we have written. So we will have 12 ei, the first 6 rows and columns will be coming from the first element. So 12 ei by L cube, the same thing which we have written after the transformation. So the transformed stiffness matrix is to be added here. And then minus 12 ei by L cube 0, and then minus 6 ei by L square. So this is the first row. Then the second row is 0 ea by L. So you are going to add basically the transformed stiffness matrix of the first element what we have got, and then minus 6 ei. So this exercise is of course trivial, but one has to do this. 0, then 4 ei by L, 6 ei by L square 0, and 2 ei by L. Then the fourth row is minus 12 bi by this should be minus 12 bi by yes, I think I have L square 0 6 ei by L square, and then here you have 12 ei by, I think this will be L cube. Okay. 12 ei by L cube, and then we have 0, and then we have 6 ei by L square. So this is for the first element. So I am adding that. So this is the basically 1 2 3 4th, and then let's look at the fifth row. So the fifth row is again 0 minus EA by L, 0 0 EA by L and 0. And then the sixth row is minus 6EI by L square, 0 2 EI by L, 6 EI by L square, 0 and 4 EI by L. So this is the contribution of basically the first element. Now let's add the contribution of the second element. So as you see, the second element is defined between global nodes 2 and 3. So it's the degrees of freedom are basically u2 v2 theta 2, u3 v3 theta 3. So the basically first row of second element will go to the fourth row, and for that is fourth. Ultimately, you can say that the 6 by 6 matrix of stiffness matrix of second element will be added to the fourth, fifth, sixth, seventh, eighth, and ninth rows and columns of the global stiffness matrix. So the additions, now you will find that we will have the first element. If you look at, so this is the first row, this is the second row, this is the third row, this is the fourth row, this is fifth, sixth, and then this will be seventh, eighth, and ninth you will have. So the contributions will start from, and this is the first column, second column, third column, fourth column, fifth column, sixth column, seventh, eighth, and ninth. So the second element stiffness matrix will go start from fourth row and fourth column. So you will find here we will have this EA by L. This is the contribution of the first element. Here we will have plus 0. So blue colors are for the stiffness matrix of the second element. So here also we will have 0, and then minus EA by L, and then we will have 0 0. So this is the contribution of first row of second element is EA by L, 0 0 minus EA by L, 0 0. So that is getting added over here. And then the second will be basically is if you look at here, so this, yeah, so this is 0 here. The first contribution is 0, and then here you will have no, just a minute. So we will have 0, yeah, 6 CI by, no, I'm adding to 1, 1, 2, 3 or 4. So now fifth one. So fifth is, yeah, 0, 0. And then here you will have plus, no, if you look at the second row of second element, so that is 0. And then we have 12 EI by L cube. So that is getting added over here. And then it is 6 EI by L square, so it is getting added here. And then you will have here basically uh, 0, and then minus 12 EI by L cube and 6 EI by L square. So this is the second row of second element getting added to the fifth row of the global stiffness matrix. Then the third row will be getting added, so we will have again plus 0 here, and then here we will have plus uh, no, in this plus you will have 6 EI by L square, and then plus 4 EI by L. So I'm adding the second basically the third row of the second element stiffness matrix. So this is 0, and then minus 6 EI by L square and 2 EI by L. Then the seventh row would become, no, it will start from seventh row, it will start from fourth column. So we will have minus EA by L, and then you have 0 0, and then you have EA by L and 0 0. Then the eighth row of the global will be fifth row of the local second element, so it would be 0 minus 12 EI by L cube minus 6 EI by L square, 0, and then you have 12 EI by L cube and minus 6 EI by L square, and then the last will be 0, 6 EI by L square, 2 EI by L, 0 minus 6 EI by L square, and 4 EI by L. So wherever there are no contribution, we put 0 there. So these will be 0. So these terms are basically 0. So this is the assembled stiffness matrix. Now similarly, if you look at the global load vector, so the first element, global load vector, we have just written. So it will go into the first four rows of the global system. So we will have here minus q naught L by 2, and then we will have 0. Then we have q naught L square by 12, and then we have minus q naught L by 2, and then we'll have again no the minus q naught L by 2, and yeah, so minus, yeah, let me just check that. So this is minus q naught L by 2. I am assembling basically this vector. So minus q naught L by 2, 0, q naught L square by 12, then minus q naught L by 2, 0. So minus q naught L by 2 I have written, then 0, and then you will have again minus q naught L square by 12. And so this is the first element. Now let's go to the second element. So the second element will go into the fourth, fifth, sixth, seventh, eighth, and ninth rows and columns. Now when you look at the for the second element, actually again the distributed load Qx is 0, only Qy is there. So you will find that there is no contribution over here. So it will be 1 2 3, so it will start from here. So this will be 0, and then this will be minus q naught L by 2. The contribution will be getting added over here, and then you will have the second term is yeah, the load is actually for the second element. If you see the way I have given, the load is actually negative because it is along the negative coordinate direction. So that is why that minus is there. So it is getting it is 0 here. Here it would be minus q naught L square by 12. So that is what will be added over there, and then we will have 0, and then again minus q naught L by 2, and q naught. So now we have first, second, third, this is fourth, this is fifth, and this will be sixth, q naught L square by 12. Because of minus, no, this term is negative, this is negative, this is negative, and this is positive because it was negative. So this is the assembled load vector, and these are the 9 basically rows: 1 1 2 3 4 5 6 7 8 and 9. So now if you look at the internal load vector, so the internal load vector, let me write, I think I need more space. So let me create that. So now the internal load vector is from the first element, what you get is minus fx11 minus no, then minus fy11 and minus m11. That's the first element, and then second, the fx21, and then you will have fy21, and you will have m21. So these are the contributions of the internal load vector from the first element. Now let's go to the second element. So second element will start from fourth row. So we will have minus f of x12, and then we will have here minus f of y12. Superscripts are the element numbers, minus m12, and then we will have fx2, fy2, and m22. So this is the assembled internal load vector. So this is what you get. So in a nutshell, you would see that the contributions of first element are going into first six rows and columns of the global system, and the contributions of the second element are going into the the fifth, sixth, seventh, eighth, and ninth, fourth, fifth, sixth, seventh, eighth, and ninth rows and columns. So that is how this assembly is done. So we call it as the global. Let's say this is the equation number one. Let me say. So now if we talk of boundary conditions, so if you talk of now the boundary conditions, so I hope everybody has followed this assembly. So this is similar to what we were doing earlier. So only thing is basically the number of rows and columns are more, otherwise it is exactly similar. But in any case, if you have any doubt, no, you can ask. If you have not followed any step how we are assembling, you can ask. You can interrupt me and no, please ask. So the boundary conditions are, now if you look at what I had said, that this end is fixed. No, this is fixed. This is node number one, and node number three is fixed. Fixed means no displacement along x, y, and no rotation about z axis. So all 3 degrees of freedom at node one and three are zero. So that is one part of the boundary condition. So boundary condition one is that u1 is equal to v1 is equal to theta 1 equal to 0, and the boundary condition 2 is u3 equal to v3 equal to theta 3 equal to 0. So because node 1 and 3 are fixed, so the displacement along global xy directions and rotation about z axis, they are all 0. And the third boundary condition is about the the node 2, global node 2. So this is, if you look at node 2, so there are no concentrated forces and moments. If there are concentrated forces and moments, then we will have different situation. So it is similar to no concentrated forces for the problem at hand, and there can be, in general, there are no concentrated forces and moments applied, externally applied. So these forces are zero. So therefore, from the equilibrium of node 2, we will find that this sum will be zero, this sum would be zero, this sum would be zero. If there was an external force along x direction, positive global x direction, then this difference would have been equal to that. So you will find that this fx2 minus fx12, this will be equal to, actually this would have been force along x direction, global x direction, but there is no force along global x direction at node 2, so therefore this is equal to 0. Similarly, we'll have fy21 minus fy12. There is no force along the global y direction at node 2, so therefore this is 0. If there was a force P applied along the global y direction at node 2, then this fy21 minus fy12 would have been equal to that P. And the last is, similarly, there is no concentrated moment, so m21 minus m12, this will also be equal to 0. If there is an externally applied moment, concentrated moment at node number 2 about positive z axis, then it would have been equal to that moment, say m, but that m is 0, so therefore this is equal to 0. So these are the boundary conditions. Now after, and you would see that although these are one typical boundary condition, you can solve, now after you have this assembled equation number one, you can solve the problem for actually different boundary condition. Both the ends could be simply supported, or one fixed, other is free. So you can have any of those boundary conditions possible, you can actually use. So now as far as the solution is concerned, so after these boundary condition, if you see the unknowns, so the unknowns are now this u2, v2, theta 2. So these are three unknowns, and then now this reaction forces fx1, fy1, m11, and this fx2, fy2, my2. So these are the 9 unknowns: 3 displacement, u2, v2, theta 2, and 6 reaction unknowns, reaction forces and reaction moments. And we have equation 1 is basically nothing but 9 equations. So these 9 equations can be solved for these 9 unknowns. So that is how now the solution will be. So now the, as far as the solution is concerned, as usual, what we do is first we solve for the displacement degrees of freedom. So first we will solve equations fourth, fifth, and sixth equation, 1 4, 1 5, and 1 6 for the displacements u2, v2, and theta 2. So if you look at these three equations, so basically I am taking from here the fourth equation, fifth equation, and sixth equation. This into u1, which is 0, this is 0 into v1, and this is 6 ei by l square into theta 1. Theta 1 is also 0. So these remain 0. Only what you have is this term, this term, and this term. And similarly, the fifth equation, this term, this term, and this term. And sixth equation, this term, this term, and this term. So ultimately, this equation 4, 5, and 6 are reduced to 12 ei by l cube plus ea by l 0 and 6 ei by l square, and the fifth equation is 0, and then you have ea by l plus 12 ei by l cube and 6 ei by l square. I am taking now fifth equation. If you take the sixth equation, first three rows and last three rows, sorry, first three columns and last three columns get eliminated because u1, v1, theta 1 are 0, u3, v3, and theta 3 are 0. So we just get only the fifth, fourth, fifth, and sixth columns of basically the fourth, fifth, and sixth rows. So we'll have 6 ei, the last one is 6 ei by l square, 6 ei by l square, and 8 ei by l. And here the unknown degrees of freedom are now u2, v2, and theta 2. And the right hand side you will see only what we will be left with is q naught l by 2 minus q naught l by 2, and then minus q naught l square by 12 minus q naught l square by 12. So that will become 6. So this is what we will have. Let us say this is equation number 2. So now what you will have to do is I am leaving no as an exercise for you, that is solve from this equation u2, v2, and theta 2. So you will have to solve. So what you can do is from the no the what you can actually do is you can express u2 in terms of theta 2 from the first equation, and you can express v2 in terms of theta 2 from the second equation, and then substitute that in the third equation over here, this equation, and solve for theta 2, and then you get u2 and v2. So that is how you will solve. So solve equation 2 for u2, v2, and theta 2. So this is a exercise for you. You should this is similar to what we have done earlier. And then now we'll have to find out the reaction forces. So how do we get the reaction forces? So now if reaction forces are no, these are the reaction forces. I said no, fx1, fy1, and m11. These are the no in the first element as you see over here. So we need to find these fx1, fy1, m11. These are the directions as indicated over here. So now you can solve for first equation for fx1, because now all the displacements are known. Only unknown would be in the first equation fx1, and similarly a second equation you can find out fy1, third equation m11, then the seventh equation you can solve for fx2, eighth equation for fy2, and ninth equation for m22. So that is how you will use these equations. So you can solve equations 1 1 1 1 2 1 3 for f yeah, you can solve for fx1, fy1, and m11. So that I already said this equation we will use for this 1 2 you will use for fy1, and 1 3 will use for m11. And then I know you will use equations 7 8 and 9. So 1 7, 1 8, and 1 9 you will solve for basically fx2, fy2, and m22. So from this you will get the complete reaction unknowns. And once you have got this information, yeah, I am leaving this as an homework for you. So you'll have to solve. First you get u2, v2, theta 2, then get these variables, and from equation 1 2 and 3, and these from the equation 7, 8 and 9. And then the post processing. So post processing, now element wise. So first element, we have been doing this for earlier, so it's the same thing I'm repeating. I think subsequently I will not be doing all these steps in detail. You have to do no, on your own. You should be able to do, because by then by now I have demonstrated enough number of examples. So if you look at the first element, this is the element. This is its node number 1, local and global both. The coordinate axes are, this is the global x-axis, this is global y-axis, this is the global local x-axis, and this is the global y-axis. And the degrees of freedom, now if you look at basically the now for the post processing, we need the degrees of freedom in the local coordinate system. So we need this dE. So dE, which is nothing but basically no u naught 1 1 v 1 1 theta 1 1 u naught 2 1 v 2 1 and theta 2 1. So this is your vector dE. So this is nothing but, we have already said, this is t into dE, and that can be written as no, T transformation matrix for element 1 we have already defined. And dE, when you look at the degrees of freedom for the first element in terms of the global coordinate system, so first 3 degrees of freedom are already 0, and you need to solve for no, so in terms of the local degrees of freedom, when you look at this is you are going to get no, so now if you look at this dE, so we'll have t into the first 3 degrees of freedom are already 0, and then you will have u2, v2 and theta 2 in terms of the global degrees of freedom. And the way we have already defined no, the T matrix, so if you multiply, you will get this as 0 0 0, and then you will get this as v2, this as minus u2, and theta will remain same. So these two are getting interchanged, and this is with a minus sign. So these are the local degrees of freedom. Now we need to interpolate u naught and v both. So as you know, u naught is nothing but 1 minus x by L, the interpolation functions, into u naught 1 for the element 1, not E. So now E is 1, so element number 1. So that is basically element number 1, and plus x by L, second shape function, into u naught 2 for the element 1. And as you see over here, u naught 1 is 0 and u naught 2 is equal to v2. So therefore this is 0, and simply this becomes basically x by L into v2, because u naught 2 is v2. As you see over here, u naught 1 is 0 and u naught 2 is v2, so you get this as an expression. So if you look at derivative for the purpose of calculating strain, du naught by dx would be equal to, we differentiate this, so x goes, you simply get this as v2 by L. And so similarly, if you look at v is the, in terms of these Hermite interpolation functions h1, h2, h3 and h4 into the degrees of freedom, corresponding degrees of freedom. So that is v11 theta 11 and v2 1 and theta 2 1. So corresponding to these degrees of freedom, already we know here that no, this is v1 and this is theta 1, so they are 0. v2 is minus u2 and theta 2 is no this. So you will finally get this as because v1 and theta 1 are 0, so h1 h2 go, so you will get no, this v2 is minus u2, so this will be minus h3 into u2, and plus you will have h4 into theta 2, the global degree of freedom. So from this, of course, you can calculate v at any location, and then the strain expression, we need d2v by dx square. So that would be minus d2 h3 by dx square into u2 plus d2 h4 by dx square into theta. So from this you will calculate d2v by dx square, and then now you will calculate sigma xx. Sigma xx will be E times epsilon xx, and epsilon xx is, we know that this is E into du naught by dx minus we have y, the local y coordinate, into d2v by dx square. So from this you can calculate stress at any point within the element, that is at any capital X value and at any y of no either the top surface or the bottom surface. So basically y equal to plus h by 2 or minus h by 2. So from this you can do the all the post processing calculations. Now if you look at the no similarly the post processing for element number 2. So if you look at the element number 2, no, you know the for the element 2, because we have said transformation matrix T is identity matrix. So that was basically 1 0 0 and so on. So we have said that this is identity matrix. So if you look at the DE, no, for the element number 2, if you look at no this DE, so D for the element number 2, which will consist of U0 1 2, V1 2, theta 1 2, U0 2 2, V2 2 and theta 2. So these will be corresponding to, simply because T is an identity matrix, so these will be corresponding to global degrees of freedom. So U0 2 would be equal to U2, V1 2 will be equal to V2, and this would be equal to theta 2, and these will be 0 because U3, V3 and theta 3 are 0. So this will be 0 0 after the transformation. So these are the degrees of freedom. And once you have got this, so then you can write U0 for element 2, which would be 1 minus x by L into U0 1 for element 2 plus x by L into U0 2 for element number 2, and this will be, because this is already 0, so the 1 minus x by L into U2. And then you of course can calculate du0 by dx. So du0 by dx would be equal to minus u2 by L. And then similarly you will write v, which would be equal to h1 into v1 2 plus h2 into theta 1 2 plus h3 into v2 2 plus h4 into theta 2 2. So this is what you will have. Now if you put all the non-zero values over here, so we will get h1 into v2 plus h2 into theta 2, and these are 0 because they are corresponding to, so this is 0 and this is 0 for the third node. So we'll get this, and then from this you can calculate d2v by dx square, which would be d2 h1 by dx square into this is not small v, this is capital V. So let me correct that. So this is yeah, this is capital V2. So this is also capital V2 plus d2 h2 by dx square into theta 2. So these are straightforward calculations, and once you have done this, so then you can calculate basically in a similar manner the way we did for the first element. You can calculate epsilon xx and sigma xx at any point within the element. So yeah, this is what basically you do know in this whole example. So this is all the steps of, so the application of the trust the frame element for solving the frame problems. The frame means actually the members would be subjected to because of the action of one member or the other or the external forces, they would be subjected to both shear force, axial force and bending moment. So for that we will solve this problem. Now a bit of modeling tips. So when you are doing modeling, either you are doing hand calculations, or you're writing your own programs in MATLAB, or using a software. So I just want to give you some modeling tips. So when you are modeling, so modeling tips. So basically members connected with pin joints. So now we have discussed truss element and frame element. After the transformation we have truss element, which has got 2 degrees of freedom at each node, u and v, capital U and capital V, and frame element which has got degrees of freedom capital U, capital V and theta. So where to choose which one? That's the question what I want to answer through this. So if you look at the members in the truss, we have already said members connected with pin joints. these members would be actually free to rotate. So no, the straight members, if there are all the joints are pin joints, then the straight members will remain actually straight. So they are, you can say, free to rotate. So they are free to rotate. And so if they are free to rotate, that means whatever external forces are coming, they are registered by only axial forces in the local element coordinate system. So you can say that external forces are registered by axial forces only, axial forces only. So you will model, so such members you will model using truss element, model using truss element. Because if you model a truss structure using beam, so then you are basically assuming that at the common joints they are not free to rotate. No, the relative rotation is not allowed. So that will give you a wrong result, because the members they are connected through pin joints. So they therefore know, if you model using frame element, they will give wrong results. I mean, but of course, if you are modeling similarly, if they are connected, rigidly connected, say belted and things like that, and the members are not concurrent, and then if you model that using truss element, that will also give you wrong results. So you'll have to appropriately choose this. So let me just give an example. Suppose you have, so we have solved this problem actually earlier. So this is a truss structure, and here all the joints are pin joints. As you see, I am taking a simpler example. You could have, this joint is also a pin joint, this is a pin joint, and there can be forces along x and y direction over here. So now if this is so, both these members are they remain straight after deformation. They are free to rotate and remain straight, because all joints are here pin joints. This is a pin joint, this is a pin joint, this is a pin joint. So they can rotate. There is no basically the members will not become curved after deformation. So they remain straight after deformation. Remain straight after deformation. So that means if they remain straight after deformation, they will not remain in the same position, but they will remain straight. So that after they move, of course there has to be displacements, but they will remain straight. So if they remain straight means no bending, and no bending means you model them using truss element. So that's one. Now let us take another example. Suppose now I take one member. No, this member is pin connected over here. It is connected through a pin joint, and this another member. So it is going like this over here, and here also there is a pin joint. So this is a pin joint, and the forces are no in this direction, x and y direction, there are forces, but this side, no, this member is actually fixed. So it's more or less same as this. Only difference is that this joint is instead of a pin joint, this is a fixed joint. So if this remain, if this is fixed here, then its rotation is not allowed, and if its rotation is not allowed, this has to be modeled using frame element. So this particular member you have to model using frame element, and this particular member you have to model using truss element with 2 degrees of freedom. That is capital U and capital V. Whereas this element has to account for bending, so you'll have to model this using element with capital degrees of freedom capital U, capital V, and theta. So this will be still modeled as no truss, that is no bending, and therefore truss. But as far as this element is concerned, it is not free to rotate, and therefore model using frame element. Model using frame element. So these will serve some guidelines for modeling this kind of structures. So yeah, so I think let me also give you some homework problems. So yeah, there are you have to work, of course. Uh, I am giving you some homework problems. So number one is, let us say, these are to know you basically learn the application of frame element. So this is one member and it is fixed over here, and this is the other member over here, and this is fixed over here, and this is a rigid joint. Here no, the joint is a belted joint. Now if you look at, if we model this also using two elements, and the forces are, let us say, only the force is capital P over here. So now the for the let's call this as element number 1 and this as element number 2. The global nodes are, this is node number 1, node number 2, this is node number 3. So these are the global node numbers, and the Young's modulus is E. Cross sectional area is the area moment of inertia is I, cross sectional area is A, and length is say L. Similarly for this, Young's modulus is E, area moment of inertia is I, cross sectional area is A, length is L. So both are identical, and this angle is 45 degrees. So for the first element, you will have this as global x and local x. This will be no, local y and global y, both would be same. And now when you look at the, so global x is no, this is a global x and this is a global y. These are same for both the elements. Now for the second element, what you can have is, this will be your local x axis, this then will be local y axis, and this is of course is the global x axis. So for element number 2, this will be angle alpha. So this will be alpha for the second element. So if you look at for this problem, when you are doing solving this, so you need to do the transformation. For element 1, alpha is 0. So the stiffness transformed, and without transformation, the stiffness matrix is going to be same. If you look at element number 2, the way I have indicated the coordinate axis, so for element number 2, alpha will be equal to now this angle, which would be 180 plus 45, or it can also be written as minus of 180 minus 45. So this is the angle alpha. So accordingly, you have to develop the transformation matrix, and after the transformation matrix, you have to assemble and the impose the boundary condition. So if you look at the boundary condition for this element, I am just giving you some hints, but no, you have to solve this as a homework problem. So the boundary conditions will be: node 1 is fixed, so u1 is equal to v1 equal to theta 1 equal to 0. Node 3 is fixed, so u3 equal to v3 equal to theta 3 equal to 0. And if you look at node number 2, so and of course the q is no, qx and qy is 0 for both the elements. There are no distributed forces applied, and at node 2, the common node number 2, there is no force applied along the x direction, externally applied force. So fx2 minus fx12, this would be equal to 0, and then you will have fy21 minus fy12, this will be equal to minus p, because at node 2 there is a force p along the negative global y direction. So that is why this minus p, and of course we will have m21 minus m12. There is no concentrated moment, so this will also be equal to 0. So yeah, try solving. These are problems as homework problems, so you must solve these problems. Now the second problem is little more complicated, frame problem. So let us say we have this kind of a frame structure. And again, let us say the boundary conditions are that these are fixed over here, and be discretized each using one element. So this is a global node 1, this is global node 2, global node 3, global node number 4. Elements are 1, 2, and this is element number 3. The forces are in this case you are having the distributed forces, although there can be concentrated forces, anything like that. So this is q naught, and no, in this element, let us say also there is a distributed force, so this is also q naught. As far as the coordinate systems are concerned, so this is global, let us say this is global x, this is global y. For element 1, this will be global x, local x and local y. So this will be local x and local y. Alpha will be 90 degrees. So now if you look at, so you can identify alpha is 90 degrees. This is similar to what we did already. So this is local x for the element 2, local y for element 2, and they're also same as global and x and y. So basically you will see that alpha is equal to 0 for the second element. For the third element, global xr, this is global x, global xy remains same for all the element, but the local x-axis, this is local x for the no the second element, and the local y for the second element is going to be no, you are rotating that, so this will become global y. So alpha will be equal to basically 270 for this, no, the third element. So I'm not going to write all of that. No, you can do that. You will see that no, E, I, A and L are same for all elements, and you are discretizing this whole thing into basically no one element each. So there are total basically three elements. And if you look at qx is equal to 0 for all, and qy is equal to minus q naught for elements 1 and 2, and qy equal to qx is 0 for all, qy equal to 0 for element 3. So that is one. And I'm just want to tell you the boundary conditions. So in this case the boundary conditions are going to be just let me tell you the boundary conditions, so that when you solve this, these hints will give you some idea how to go about this. So the boundary conditions are that first node is fixed, so u1 is equal to v1 is equal to theta 1 equal to 0, and similarly the fourth node is fixed, so you will have u4 is equal to v4 is equal to theta 4 is equal to 0. And now the if you look at common nodes 2 and 3, so there are no externally applied loads over there. So at node 2, these are global node 2, you will have fx21 minus fx12, this will be equal to 0, no external force along positive global x direction. Similarly fy21 superscript is element number, and fy12, this is also 0 because there is no external applied concentrated force at node number 2. And then if you look at there is no concentrated moment also, so m21 minus m12 will be equal to 0. And the last is at node 3. If you look at the this internal loads, there would be from element 2 and 3, so fx2 2 minus fx13, this will be equal to 0, and fy2 at 2 minus fy13 will be equal to 0. Superscripts are now the element numbers, so element numbers are coming as 2 and 3 because at node 3 elements 2 and 3 are connected, so that is how it is coming. And m22 minus m13, this will be equal to 0. So these are the boundary conditions. So this is how you will be solving these problems. So please do all the homework problems, whatever homework I am giving, you must do that. So yeah, I want to stop here, and know if you have any doubts and questions, yeah, you can ask. So yeah, I think that's where I want to stop. If you have any questions and doubts, you can ask. So today we completely discussed the application. So application of frame element, how to use frame element for solving different types of problems. Yeah. So are there any questions, doubts? Okay. So then thank you all for your attention. I'm stopping here. Thank you all. Thank you very much.